Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome again to Power Electronics. This is Raid Al Malki. Today, inshallah, we will address an important topic which is regarding controlled rectifiers. Again, this is a controlled rectifier, right? Here, controlled rectifier, three-phase, half-wave, and full-wave controlled rectifier. This is the last topic for the rectifiers. We have taken single phase, half wave uncontrolled. We have taken single phase, full wave uncontrolled. We have taken also three phase, half wave, and full wave uncontrolled rectifiers. We also mentioned single phase, half wave controlled one, and we reached to full wave, single phase controlled. Then today, inshallah, we will go through the three-phase, half-wave, and full-wave controlled rectifiers. Now, this is the topic for today: three-phase, half-wave, and full-wave controlled rectifier. And also, I am insisting on the word here, which is controlled, right? So we will use a thyristor, a gate. We will give the signal to the gate in order to operate alpha, to control alpha, right? So we will outline some important things, and we will go for example also. Now let's go to the first slide here. Now, as you can see here, shabab, three-phase is basically three-phase half-wave controlled rectifier is basically having, can you see here, shabab, on the right side? It's basically having three-phase supply AC, right? And we have load here, right? And the voltage here should be in DC, right? This is AC, this is DC. In between, shabab, we have three thyristors here, three thyristors. Previously we have taken half wave uncontrolled rectifier, three phase half wave uncontrolled rectifier. We used diode, right? So the output alpha is not controlled. So we start from 0 up to 180 and so on. Okay, here we are controlling the thyristor by a gate signal. Now forget about this part here, shabab, because this one is a star delta transformer, star transformer. This is not required for you in this course, but make sure that you understand that we have three-phase supply AC. We need to convert it into DC supply using half-wave controlled rectifier. Now let's go back here, shabab, and let us see what does it say here, shabab. Now, he said three-phase have a wide range of applications, like what? Like high voltage DC. So high voltage DC transmission system, basically it is transferring DC power from one location to a very far location, like from Dammam to Jeddah, for instance. So we will use high voltage DC transmission line. You used to three-phase, right? You used to AC transmission line. Now for this example, we can use three-phase half-wave or full-wave rectifier. Basically, it is full-wave rectifier in order to transmit the power from one location to another using high-voltage DC system. And also we have many applications like this, like controlling motor drive, traction equipment, and so on. Now we will concentrate on the classification of the commutation here. As you can see, we have two categories: line commutated control rectifier, which is thyristor rectifier, as we have here, and also we have force commutated pulse width modulation. We will not go through this part for now. We will just use the thyristor rectifier. We will use the thyristor rectifier. Now let's go here. For this part is explaining the three-phase half-wave rectifier. Now, this topology is used to control the load voltage. The half-wave rectifier uses three common cathode thyristor, okay, arrangement. Okay, in this figure, the transformer are assumed ideal, so we don't use. I told you don't focus on the transformer now because it is not required in your course. The thyristor will conduct on state when the anode to cathode voltage VAK is positive and the firing current pulse IG is applied. So this one is already explained in the previous lectures. We said that in thyristor here, this is thyristor, right? This is anode, this is cathode. So if you have a voltage, okay, applied here, V voltage applied to the anode, positive to the anode and negative to the cathode, we explained that we will have a forward bias diode, right? You remember, forward bias, and then the diode will conduct. Now for the thyristor, I already explained last lecture that we have here something called gate. Okay, so this gate, we will apply a small pulse here يا شباب in order to fire the thyristor, fire on the thyristor. So that in this way we can control how much power being transferred from or being controlled from AC into DC, right? Now let's go to the next slide. Now he said the firing angle is measured from crossing here شباب, follow me, from crossing point between the phase supply voltages. Now here يا شباب, on the right hand here يا شباب, this graph here, you remember this graph is used for the half-wave, three-phase half-wave control uncontrolled rectifier. So as you can see here, we have, this is line A, right? This is line B, and this is line C here. Okay, it will stop here, it will complete here. So this is the output of the three-phase half-wave uncontrolled rectifier, and alpha here, alpha, you remember alpha يا شباب, alpha here is it was 30 degree, right? And here beta it was equal to 150, right, degrees. This is the omega t, according to omega t, right? And this is the output voltage that we get from the three-phase half-wave uncontrolled rectifier. Now the case is a little bit different, and sometimes it is confusing. If you look here يا شباب, now here he said shows that the positive the possible range for getting delay in between alpha is 0 and 180, okay? But because of the commutation problems in the actual situation, the maximum firing angle is limited to around 160. Now the thyristor goes to the non-conducting conditions of off state when the following thyristor is switched on or the current tries to reach the negative value. So if the current goes to the negative value, or we reverse the power the voltage on the thyristor, then we will or we open the circuit after the thyristor, then the thyristor will go off in non-conducting condition. Now this is the remember this is how to find this is how, sorry, let me just do it again. Now this is how to find V output DC. This is V output DC. In this case يا شباب, this is the after the derivation of this equation here, then we will find that the V maximum multiplied by sine pi over 3. Where is sine pi over 3 يا شباب? Yes, sine pi over 3, which is 30 degree, divided by pi over 3, and this is basically like the half wave. Can you see here يا شباب? This formula, you remember this formula شباب? It was like this. So in the half wave uncontrolled rectifier, we have this part here. Okay, but here in the controlled rectifier, we just only multiply by cosine alpha. Or we can change the color here, right? Let me change the color here. So we can just add this term to the previous formula for the half wave uncontrolled. Then if we multiply by cosine alpha, then we will get the three-phase controlled rectifier, V out. Okay, so basically it is the same thing here. So if you get this value, it is the same as the formula here. 3 multiplied root 3 divided by 2 pi. Okay, so this is the same thing here. Okay, the only difference between three-phase uncontrolled and the controlled rectifier is just only multiplying by cosine alpha. This is the only difference between them. Okay, now let's go to the next slide. Now this is the basic configuration for the three-phase half wave controlled rectifier. As you can see here, we have 3 lines يا شباب and the neutral. Line 1, line 2, line 3, and the neutral. Then also we have the 3 thyristors here يا شباب, and we will get the V load here. This is V out. This is the V out. Now, in this graph, he said that the angle at above above 90 degree. So this is 90 degree. Remember, يا شباب, it is above 90 degree. So we will have discontinuous current, or this is voltage. So it's the same. So we will the thyristor is going to conduct. This is alpha approximately 120 degree. Approximately 120. So after 120 degree, the diode is going to conduct, right? And we will have an output voltage. Now this is the output voltage, okay? And up to here يا شباب. And this is the remaining part for thyristor number 3. شباب, this is very important in order to understand how we get the output, V output شباب. Here guys, we have figure 12.2 and 12.3. 12.2 is basically having 3 lines يا شباب. Let me draw the VA first. This is VA. I'm going to change the color for I'm going to use the blue, right? So this is the blue for the for P here يا شباب. The second line يا شباب. This is the second line. I'm going to change the color for the third one, which is let me use green. This is line C, or line number 3. So as you can see here, we have 3 lines. Okay, now alpha is basically can be found here, and we can vary the alpha here from this part and up to here, this part يا شباب. Now this is alpha, so from here it's alpha approximately pi over 3, or yeah, and then this area can be found for the V out. So V out here, and also we will find that this area approximately to this area, then we can find the V maximum. This is the V maximum here يا شباب. Instantaneous DC voltage VD, this is the instantaneous here, from here to here. This is the instantaneous voltage. So up to here يا شباب, this is the instantaneous voltage. Now the average DC voltage is VD, right? And this is the VD here يا شباب. Let me use another color. No. Okay, this is the VD يا شباب, this is the VD. And so on. Okay, this is the average voltage. The firing angle here should be alpha. This is the firing angle. Here يا شباب, this is the possible range for getting delay. Remember we had I told you that we can vary alpha between 0 and 180, and here as you can see we did not start from 0 and we did not reach to 180 because this is not possible and practical. So this is the area that we can adjust alpha in between. So approximately here like pi over 3 up to 180 here, 160 degree. So here 30 degree. Let me just make them the same. We will use degree here, not radian. So from 30 up to 160, this is the possible range for alpha. This is the possible range for alpha. Now after that we will not get output and we will have issues in the system. So practically it is not it's not possible, and you can search for the why it's not possible. You can search the internet and you will find the answer. Now here guys, we have the three-phase half-wave controlled rectifier. As you can see here, we have two yes, we have here waveform. This is for the waveforms for the resistive load only, and on the right side we have with the resistive load with resistor and inductive load. Okay, now let us focus on the resistive load first, and we will see how the waveform is acting, right? Now previously in the three-phase half-wave uncontrolled rectifier, our alpha was 30, right? Remember شباب, it was 30 and it will finish at 150. Now in three-phase half-wave rectifier, controlled rectifier, if we have alpha is 0, so it will act like the uncontrolled one. Okay, now this is like the uncontrolled one. It is easy, nothing is different. But here we have something very important to mention. Now in the uncontrolled rectifier, we said alpha is 30 degree. Now here is different. We said like this because it was uncontrolled one. Now this is the scale يا شباب. This is the scale. This scale is for what يا شباب? For omega t. Now alpha is 0 means when omega t is 30 degrees, then alpha is equal to what? Alpha is equal to 0 degree. So when omega t is 30 degree, then alpha is 0. Okay, so it is a little bit confusing, but we will not use the range anymore here. This is the range يا شباب of the omega t, the angular frequency with time. So if now here we have alpha is 0 يا شباب, alpha is 0 because we did not change alpha, right? We did not fire because we have a thyristor. We have a thyristor, and we said in three-phase system we will start from 30 degree, right شباب? So this is 30 degree, and this is for up to here يا شباب. This is 360, and this is the rest of the waveform. So we can say this is Q1, this is Q2, and this is Q3. The rest of the Q3 is here. Okay, so if alpha is 0, so alpha here is 0, right? Now let me erase here يا شباب. Now this is simple. Let's go for the other waveform, but I'm going to keep this one here يا شباب to make sure that you understand. Now let me just take the ruler. I'm going to draw line يا شباب for the 30 degree, and let us see how the waveform is acting يا شباب. Okay, let me use the black, yes, the black one. So I'm going to draw a line. This is at 30, and we know the waveform it should end at 150, right? So this is 150. So we can draw a line here also. So this is for Q1 only, right? Now we can add also 120 degree. So 150 plus 120 degree, how much is about? 150 plus 120, 270. So we can draw a line here, 270, right? And also we can this is we can add 270 plus 120 is 390, or we can say, because we should stop at 360 and plus 30 at the beginning. So this is the waveform. Okay, now here we can write يا شباب. Okay, here we can write alpha is 0 for what? For Q1. Alpha 1, we can say alpha 1. Here for this line, we can say alpha 2 is equal to 0, right? For Q2. Here for the third line, we can say alpha 3 is 0 angle, of course. These are angles, and this is for Q3 at 360, and the rest is here as I showed you before. Now this is alpha at 0. Now let us check for the when alpha is at 15 degrees. Okay, so we can say this is alpha, right? Here يا شباب, so alpha here is 0, and here if we add 15 to 30 it will be 45, so this is 35. So we can draw a line from the beginning of the waveform يا شباب up to our 15 degree. Okay, then it will complete with the waveform. Okay, this is 0, right? We will add 15 degree and we will go up again, and we stop here. We go for 15 degree, and we can complete شباب here up to 360, and we will complete the rest here شباب. Now here alpha is equal to 15 degree, alpha 1. Alpha 2 is 15 degree also. Alpha 3 is equal to 15 degrees. So this is the way, شباب. This is the way how to draw. Now let us go for 30. Let me change the color for the green. Now if alpha is 30 degrees, now we can start. Now we know this is alpha here. So alpha here is 0, but we said 60. So alpha we need to add 30 degrees. So we start, okay, we start the line like this, and we add 30 degrees. So 30 plus 30 is 60. So we will go up to 60 يا شباب. Then we can go up, right? We'll go down until this point. Now this point is alpha 2 is 0. Alpha 2 is 0 here, right? We will add 30 degrees. Now this is alpha 0. We will add 30 degree and we can add like this. And then we go up. We will go up to here يا شباب. This is alpha 3 is 0. We will add 30 degree also. And this is how to add 30 degree. And we will stop of course at 360 because we need one cycle. And this is the complete here يا شباب on the left side. This is the complete part of the third thyristor, right? Now I'm going fast شباب because I think it is clear. Now let me go for the if alpha is 60. Now this is very important شباب. This is very important. Now remember that we are working for the resistive load only. If we have resistive load only. Now as we said alpha here يا شباب is 0, right? Alpha is 0. We need to add 60 degrees. So we will go like this with the line. Okay, now if this is 0, right? Up to here is 30 degree. Alpha is 30, right? Up to here is 60. Now why we draw like this line and we didn't go like this يا شباب؟ ليش ما رحنا كده طلعنا فوق مرة ثانية؟ Now this is a very good question, and the its answer is very clear, because we cannot go to negative because this is resistive load. It is not inductive load. It will not charge يا شباب anything. So this is a resistive load, so it will go 0 up to the next firing angle, which is 60 degree, right? Then we will go up. We'll go like this down until this is alpha 2 is 0, and here 30, right? And we'll go, we should go like this صح شباب؟ بس this is wrong. We'll go up, we will add 30 again, then we go up, then we go down until alpha is 0, but we need alpha 60, right? Alpha 3 is 60, so we will add 30 and 30, and then we can go up. Clear يا شباب? Up to like this 360. This is one cycle, and the completion is here يا شباب with the waveform. Now this is for the inductive load only. Now if we go for resistive load, for resistive and inductive load, now we will see the comparison here يا شباب. Now I'm going to use the same color. We used green for 30 degree, right? So 30 degree here if we have inductive load. Now we can start يا شباب. As we said, alpha is 30, right? So alpha here is 30. We can draw a line, and this is alpha 0, right? And we can go here. We add 30. This is 60. So we can start from here, and we go back like this. We know alpha here is 0, right? At 150. Alpha 2 is 0. And we can add 30 degrees. Now we add 30 degree like this, and we go up, and so on. Here is 0. We add 30 degree and up to 360, right? This is at 30 degree. Now, is there a difference between 30 here, 30, between this line يا شباب, this waveform and this waveform? Is there any difference? No, there is no obvious difference between those lines because it is at 30 and we do not go for the negative يا شباب. We do not go for negative. Now let us see 60 يا شباب. Now this is 60. We used what color يا شباب? The blue color. Okay. The light blue here. Now we will go up to omega t is 30, which is alpha is 0. Alpha here is 0, right? If you want, we can draw a line يا شباب. I'm going to use another color. let me use this gray. Okay. Again, we'll add like here. At 150, we will drop line here يا شباب. At 270 we'll drop line. Okay, so this is the line يا شباب. Now let us focus here يا شباب. If I drop line means this line alpha is 0, right? Now let me use the light blue color here. So we will go like here يا شباب. Then we know this is 0. We can add 60 degree, right? So this is 30 degree. Now before we used to go here يا شباب. We used to go like this. But now we have inductive load. We have inductive load. That's why we will go for the negative up to 90 degree. Then we will go up. Of course, this is an issue with the output voltage, and this is not good because we have a negative ripple, right? Now here also we can go here. This is 0, remember يا شباب, and we can add 30, and we add another 30, and then we can go up. Then we go like this, and this is 0, right? Alpha is 0 here, so alpha here is 30, alpha here is 60. So we can go like this up to yeah, this is 360. Okay, so we can stop here. Okay, and that is the rest of the. Now if we have 90 degree here يا شباب, let me use another color. We can use the okay, no, the blue here, dark blue. Now we can go from here يا شباب, and this is alpha 0 as you remember. Then we add 30 degree, and then we add 30 degree, we reach 90, and we will add 30 degree in order to reach what شباب alpha is 90 degree. Then we will go up, and we will go down here, and we will add 90 degrees. So this is 30, this is 30, this is another 30. We'll go up, we'll add 30, and so on until here يا شباب. This is 360, right? So we will stop here, and this is the rest of the waveform. خلاص. So in case if we have R load and we add alpha bigger than 90, then we will have problem يا شباب. Now let us see what the slides tell us about alpha. Now here with various loads, if we have here يا شباب on the left side, if we have R is bigger than 0, right? And LD mean the inductive load is 0. Here we have inductive load 0. So of course, if alpha is bigger than 90, then it will go for here 0, and then it will go up, and it will go here, and it will go up, and so on, right? So this is if alpha if the inductive load is 0. Now if we have inductive load is bigger than 0, of course we will go, this is 90, right? We will go down a little bit, right? We'll go to the negative part, and we'll go up again, and then we'll go for the negative part little bit. Now in case if you have very large inductive load, large inductive load here, this is large inductive load, it means it's bigger than the previous one, right? Then we will have bigger يا شباب what? This is almost 90. We will bigger negative ripple, and we will have bigger negative ripple يا شباب. Okay, if we have very large very large inductive load, then what will happen يا شباب? We will have a very large negative ripple ولا يا شباب. Now this is not important. Now let us see the current يا شباب. Now we talked about the voltage, but we did not mention the current. Can you see here يا شباب? Now if I use red color here, the current here يا شباب, can you see the current here we have current goes to 0, then current goes to 0 if we have no inductive load, right? Here the current reaches to this part and complete a little bit 0 here يا شباب, and it will go like this and here and 0 little bit. Now this is called discontinuous current. This is called discontinuous current. Now what about this current يا شباب? If the inductive is large enough, then the current will not does not go to 0, and it will have rebel, right, like this, right? It will not go to 0 because there is no time to fully discharge the inductive load. Now if we have a very large inductive load, then there is no time to discharge, okay, and charge. That's why we will have a very straight line output current, DC current, okay? So this is of course if we have a very large inductive load. Now that's all about the half wave controlled rectifier. Now we will go for the 3-phase full wave controlled rectifier. The 3-phase full wave controlled, we have here a practical example. We have here, as you can see, we have 3-phase, right, AC. Then we have 6 diodes, right, 6 thyristors, because we are controlling the alpha here, shabab. And then this is the V out across the load. This is V out, it should be in DC. This is V in AC, right? So we are rectifying the AC source into DC source using 6 thyristor in order to rectify the signal. Now this is the typical diagram for the 3-phase full wave rectifier. We will use bridge rectifier here, shabab. Line 1 should be here between S1 and S4. Line 2 is here. Line 3 is here, so that we cannot have short circuit, right, shabab? And then of course in one cycle we will have 2 diodes working together, right? Remember, like the one that we have before for the uncontrolled rectifier. Okay, and this side, shabab, we can find that at each 60 degree we will have 2 diodes, shabab. Then at each 30 degree, like the uncontrolled rectifier, we have 1 pulse. Now this is the V maximum, right? Here we have the V maximum. Here we have sine pi over 6 divided by pi over 6 multiply cosine. So this is, ya shabab, it's almost to 1.35. This is line to neutral. Here, shabab, concentrate here. Here we have, this is the same formula. This is the formula that we used. This is the same thing here, shabab. Now if you find this is the same formula for the 3-phase full wave uncontrolled rectifier, but we multiply only by cosine alpha in order to find the controlled one, in order to find the controlled rectifier. This is the only difference between those two, okay? Now in order to find this value, 1.35, the value here is like 3. Let me write it here, 3, because he's using here line to neutral, okay, and I'm using here what is line to line, so we will multiply by root 2. So 3 multiply root 2 V line to neutral divided by 2 pi, right? Sorry, divided by pi, because we use 3 here, or we can, because it is there are 6 diodes, so we can use 6 divided by 2 pi. Okay, so if we add this in the calculator, if you have your calculator with you, so we can multiply 6 multiply root 2 square root of 2 divided by 2 pi. Yes, the answer is 1.35. So the answer is 1.35. This is correct. So this is correct. Okay. Now the importance of this waveform يا شباب that we have smoothing the DC voltage ripple is also smaller than the one generated by the half-wave rectifier due to the absence of the third harmonic, and this is not very important for you, but of course if we increasing the number of ripple, if we increasing the number sorry, yeah, if we smoothing the DC voltage rebel, then we will get smoothing output voltage, right? And the more number of rebels, the smaller number of rebels, we will have smoother current يا شباب. Smoother voltage. I mean that يا شباب, if we have, this is the waveform of three phase half wave. Right, شباب. Now in our case here, if we have three phase full wave, then we have like this. Then it will be smoother يا شباب. It will be smoother. Now let us concentrate here. As we said يا شباب, do not focus on the the transformer here. We have three winding transformer. This is very advanced for you يا شباب, so forget about it now. Just focus that we have three phase inputs, and we'll go through the thyristors here, and then we will have this is the V out. This is the V out DC, right? So here يا شباب the waveform for the AC current of the 6 pulse rectifier. So we can 6 pulse means we have three lines, and we have six we have VA, VB, VC, and we have V1, V2, V3 because of the negative part of the supply. صح ولا شباب? So this is the first one يا شباب. So if the alpha here, this is alpha, he introduced you alpha here يا شباب. So alpha here approximately 30 degrees. So we can start from here. Okay, then it will go we'll go down 30 degree, and we'll go up. We'll go up to here. This is alpha here is 0, and we'll add 30 degree, and then we can go up, and we will go up to here, and then we'll add 0, and we add 30, sorry, and we'll go up, and so on. This is how to find the three phase full wave controlled. Now we can complete the cycle يا شباب. This is fourth one, fifth one, and this is 30 degree here, 360 here. We should have 360 degrees, and this is the rest of the waveform. Okay, this is the rest of the waveform. Now let's go for the example. Here we have an example 4-13 from the textbook. He said controlled three-phase rectifier. Three-phase controlled rectifier has an input voltage of 480 volt RMS at 60 hertz. The load is modeled as a series resistor with inductor inductance with resistive load is 10 ohm, and the inductance is 50 millihenry. Determine the delay angle required to produce the average current of, so this is out, right? This is the average current. So this is I out. I out is 50 ampere. Of course it is DC, right? So he needs the alpha. So we can compute this formula يا شباب in order to find what يا شباب the V out. So we know that V out for the full wave, huh? For the full wave, we know that it is 3 V maximum line to line divided by pi, right? Multiply by cosine alpha. From this we need alpha يا شباب. So we can divide, so cosine alpha equal to, cosine alpha is equal to, so we can divide here يا شباب, 3v maximum line to line divided by pi, and this will go over here, and here also we divide by 3 v maximum line to line divided by pi. So this one is going up, and this one is it will remain down. So it will be cosine alpha is equal to v out pi divided by 3 v maximum line to line, right? Now if we need alpha cosine inverse, this value v out pi divided by 3 v maximum line to line, and we know that line to line we should multiply by root 2, don't forget that يا شباب, in order to find it. So if we apply this formula here يا شباب, then we will get alpha is 39. So we need to fire alpha at 39.5 degrees in order to get 50 ampere DC current as output. Clear يا شباب? I hope it's clear. This is how to find the alpha here يا شباب. This is a very good example, and you can practice some more examples from the textbook. Thank you so much for attending this lecture, and stay safe.